The dot product or the scalar product between two vectors is one way of multiplying vectors and is defined as the product of the magnitudes of both vectors by the cosine of the angle between them. So in this case, f cosine theta can be seen as the magnitude of the orthogonal projection of the vector f in the direction of vector d. And similarly, if we take the dot product in reverse, well, that's equal to the product of the magnitudes of both vectors by the cosine of the angle between them. So in this case, d cosine theta can be visualized as the magnitude of the orthogonal projection of vector d in the direction of vector f. So the vector dot product is commutative because these give the same result, and we can also write the dot product as the sum of the products of the components of the vectors, so in this case in two-dimensional Cartesian coordinates. We can use the dot product to represent vectors in different coordinate systems. So for example, if we take the dot product between the force vector and the horizontal unit vector, well, by definition that's the magnitude of f by the magnitude of I, which is 1, cosine theta. So that gives the horizontal component of that vector. And similarly, we take the dot product of the vector f with the unit vector in the vertical direction. So by definition of the dot product, we have the magnitude of f by the magnitude of j, which is 1, by the cosine of the angle between both vectors, which is this angle over here. So that's the same thing as f sine theta. So basically we have the magnitude of the orthogonal projection of the vector in the direction of j. So you can visualize this as f being the magnitude of this vector by the sine of theta. Let's prove the vector dot product in Cartesian coordinates. So we'll first write both of these vectors in Cartesian coordinates, where theta f is the angle between the force vector and the horizontal axis. And similarly for the vector d, so theta d is the angle between the vector d and the horizontal axis, where f and d are the magnitudes of vectors f and d. And by one of the definitions of the dot product, we multiply the x and y components and sum them together. So for the x components, and multiplying the y components, and now we can factor out the product of the magnitudes of both vectors, and using our trig identity, we obtain the following expression. So theta f minus theta d is theta, which is the angle between the two vectors. The work done by a force to move a particle over a distance d is defined using the dot product between the force and distance vector. And this is for a simple case where the force does not depend on the position of the particle and the particle is displaced over a straight line. Well, as we've seen, f cosine theta is the magnitude of the orthogonal projection of vector f in the direction of vector d. So in this case, because the angle between the vectors is acute, then the work done by the force is positive. And note that it's the parallel component of the force that does work on the particle to move it over that distance. So as we can see, when the force is perpendicular to the distance vector, well, the work done by the force is 0. Because as you can imagine, when projecting that force onto the distance vector, it's going to be a point. And for the yellow force here, if we project it, it's going to act against the distance vector, and therefore in this case, the work done by the force is negative. The work done by a force F to move a particle over an infinitesimal displacement dr is defined using the dot product. So that's equal to the infinitesimal change in work. So therefore, to move the particle over some distance along a curved path, we break up this path into infinitesimal segments. So integrating both sides of this equation gives us the work done by the force over that distance. And note that in this case the force can also be a function of the position of the particle. So if we visualize the work done by the force in one dimension to move a particle from a position of xa to xb, where the force is a function of x, well, we can see that the work done by the force is the area under the position time curve. And note that in this case we're modeling the object as a particle. A block is dragged along a surface using a massless cable as shown, and the tensile force Ft has a magnitude of 3 newtons, and the kinetic friction force has a magnitude of 2 newtons. And we've drawn a free body diagram, and we're asked to determine the work done by each force if the block moves a distance of 4 meters. Well, the work done by the force of weight is equal to the work done by the normal force, which is 0 joules, because these forces are perpendicular to the distance vector. Now the work done by the tensile force is equal to the magnitude of the tensile force multiplied by the magnitude of the distance vector, which is 4, cosine of the angle between them, which is equal to 12 root 3 on 2, or 6 root 3 joules. And the work done by the friction force is equal to 2 by 4 by cosine 180 degrees, so we get a negative here, and that's equal to minus 8 joules. A ball with a mass of 2 kilos is rolled up a frictionless plane, and we're asked to find the work done by all forces if it travels 3 meters up the plane. So I've drawn in the force of weight and the normal force, and the work done by the normal force is 0 joules because it's always perpendicular to the displacement vector. Now for the force of weight, we can resolve it into tangent components and normal components to the plane, or we can use the dot product directly to evaluate the work done by the force of weight. So by the dot product, that's equal to the magnitude of the force of weight, which is the mass of the ball by gravity, and multiplied by the magnitude of the distance vector, which is 3 meters, and that's multiplied by the cosine of the angle between the two vectors, which is cosine 120 degrees. So what we obtain is 2g by 3 by minus a half, or minus 3g joules. Consider Newton's second law and the velocity and acceleration vectors in multiple dimensions. Well, the one-dimensional analogues of these equations are as follows, and now we can eliminate dt between these equations, and then substitute for ax into Newton's second law. And if we separate the variables and integrate both sides of this equation, we obtain the following expression. And this is the work-energy theorem, which states that the work done by the forces acting on a particle is equal to the change in its kinetic energy. Now if we followed the same procedure in multiple dimensions, you get the following expression, and then summing these together, you'll get the work done by the forces acting on a particle in multiple dimensions is equal to the change in its kinetic energy. So here we have the squared magnitudes of the vectors, which is the same as the dot product between a vector and itself. A 5 kilo wooden crate is dragged along a surface which has these friction coefficients and released with an initial speed of 5 meters per second. And we're asked to calculate the maximum distance traveled by the crate. So to do that, we can use the work-kinetic energy theorem. And only the force of kinetic friction does work. So that will be minus ffk multiplied by d max is equal to the change in kinetic energy, which is 1/2 by the mass of the wooden crate by the final speed squared minus the initial speed squared. So when the crate reaches a maximum distance, the final speed is 0, and the kinetic friction force is basically the kinetic friction coefficient by the normal force, which we can obtain by vertical equilibrium. So that would be the mass by gravity, and then by d max is equal to minus 1/2 mv0 squared. And substitute for the kinetic friction coefficient and the initial speed, then we can calculate d max, which is 3.2 meters. Suppose we take our origin at the surface of the Earth with a positive y direction upwards. And suppose a particle is at a position y0 in a gravitational field, so near the surface of the Earth, the force of weight is constant. And this particle is raised to a position y in the gravitational field. So the work done by the gravitational force can be obtained using the work integral, or simply applying the dot product because the path of the particle is linear and the gravitational force is constant. So because the force and distance vector oppose each other, then the work done by the gravitational force is negative, as the particle moves from a position of y0 to y in the gravitational field. So the change in gravitational potential energy is the negative of the work done by the gravitational force. So it's effectively the work done by an external agent to raise this particle from a position of y0 to y against the gravitational field. Suppose we have a mass attached to a spring, and we take the origin at the position of the mass where the spring is not deformed, and we're treating the mass as a particle. Now suppose this spring is stretched such that the mass is at a position of x0 from the origin, and we stretch it again where the mass is at a position x. Now here we're looking at a linear spring where the force in the spring is proportional to the distance from the undeformed or equilibrium position, where k is the stiffness of the spring. So the work done by the spring as the mass moves from a position of x0 to x, where the force in the spring opposes the motion of the block, is minus the force in the spring integrated with respect to x. So therefore this will give us the following result. Now the change in elastic potential energy is minus the work done by the spring as the particle moves from a position of x0 to x. Consider a particle travelling along a curved path between 2 points. And here we've drawn the forces acting on the particle where we consider friction, and the infinitesimal displacement vector is drawn as follows. And here we want to find the work done by the gravitational force, or the force of weight. Well, what we do is integrate the dot product between the force of weight and the infinitesimal displacement vector. So that will be minus mg dy, where y0 is the initial position of the particle. Well, as we can see, no matter what path the particle takes, the work done by the gravitational force is the same. So therefore the gravitational force is a conservative force, which is path independent. So if the particle takes some path and it goes back to the original position along a different path, then we say the work done by gravity along the closed path is 0. And this is true for all types of conservative forces. Consider a particle moving along a curved path from some initial position to a final position. And we're writing the infinitesimal displacement vector in Cartesian coordinates where we're considering friction between the particle and the surface. And here we have theta as the angle from the horizontal and this infinitesimal displacement vector. Now suppose we want the work done by the friction force. Well, that's the integral of the dot product between the friction force vector and the displacement vector. So if we divide through by ds and then multiply the result by ds, where ds is the length of this displacement vector, well dx ds is cosine theta and dy ds is sine theta. So this integral can now be written as follows. We obtain the following result, where cosine squared theta plus sine squared theta is 1. So therefore the work done by the friction force depends on the path that the particle takes. So we say that the friction force is not conservative or dissipative. In previous videos, we saw that the change in potential energy is equal to the negative of the work done by a conservative force. And in one dimension, this can be written as follows. So differentiating both sides, the second term on the left drops out. So therefore we have a relationship between the conservative force and the potential energy function. So recall for this spring mass system, we had the change in elastic potential energy. And if we take our reference point at the undeformed position of the spring, so x0 is 0, and therefore at the equilibrium position of the spring has no stored potential energy. So therefore we get the following potential energy function, and from this relationship we can see that the force in the spring is the negative of the slope of the tangent to the potential energy curve. So when x is positive, the spring is in tension and the force points to the left, and when x is negative, the spring is being compressed, so the force in the spring is a restoring force that brings the mass back to the equilibrium position. Given the potential energy diagram below for a harmonic oscillator, write an equation for the speed of the block in terms of the following variables. Well, the initial energy that's input into the system when the spring's initially stretched is constant and equal to the kinetic energy plus the potential energy. So E0 is always equal to 1/2 by kd squared because that's the energy input into the system, and the kinetic energy at any point in time is 1/2 mv squared plus the potential energy as a function of x as the block oscillates back and forth. So that will be the elastic potential energy stored in the spring. And then turning this equation around for the speed of the block, we get v is equal to the square root of k on m by d squared minus x squared. So x must always be less than or equal to d because you cannot have more energy in the system than what was input into it. So when the block oscillates back and forth, it can only go as far as minus d, so as to not exceed that initial energy. Given the potential energy diagram below for the harmonic oscillator, identify the equilibrium point and state whether it is stable or unstable. Well, recall that the force in the spring is equal to minus a change in potential energy. So when the slope of the tangent to the potential energy curve is 0, which is at this point, that's where the equilibrium point is. So recall that the potential energy stored in the spring is 1/2 kx squared, and therefore the force is equal to minus the derivative of this function with respect to x, so that will be minus kx. So when x is positive, the force is acting to the negative direction, and when x is negative, the force is acting towards the positive direction. So the force is always a restoring force, that tries to restore that block back to the equilibrium position, and therefore this is a point of stable equilibrium. A 1 kilo rock is launched from a slingshot, and we're asked to derive an equation for the potential energy stored in a rubber as a function of x from the graph below. So recall that the force is equal to the negative of the change in potential energy with respect to x, so minus F is equal to plus du dx. And substituting for minus F, we get e to the lambda x minus 1 is equal to du dx, and then separating the variables, we get du is equal to e to the lambda x minus 1 dx. And then integrating both sides, and we integrate from 0 to x, so therefore the potential energy is equal to 1 on lambda e to the lambda x minus x evaluated from 0 to x, and therefore u of x is equal to 1 on lambda e to the lambda x minus x minus 1 on lambda. A 1 kilo rock is launched from a slingshot from an initial position of 15 centimeters, and we're asked to find the speed of the rock when it reaches 10 centimeters, and we have the potential energy function. So the initial energy input into the system remains constant, so that's u at point 15, and that's equal to the kinetic energy of the rock, which is 1/2 by the mass by the speed squared, plus the potential energy of the rock when it reaches 10 centimeters. And therefore if you evaluate u of 0.15 and subtract u of 0.1 from it, and flip this equation around, you're going to get the speed of the rock is 2.1 meters per second. The potential energy of a particle attached to a nonlinear spring is plotted below, and we're asked to calculate the equilibrium positions of the particle and state if they are stable. So we know that the force is minus the slope of the potential energy curve, which is equal to minus 1 plus 3 by x minus 2 squared. And if you set the force to 0, you're going to get two solutions to this equation. And that's going to give you the equilibrium points, which are at x is equal to 2 plus or minus 1 on root 3 meters. And now for this equilibrium point, we can see that the slope of the tangent to the curve is negative, so therefore the force is positive. So it's going to point in a positive direction. And on this side, the slope of the tangent to the curve is positive, so the force is going to point to the negative direction. So therefore the force is a restoring force, pulling that particle towards equilibrium. Recall the work energy theorem, which says that the work done by a set of forces acting on a particle is equal to the change in its kinetic energy. So we can break the work up as the work due to conservative forces and the work done due to dissipative forces. And the conservative forces we looked at is gravity, and we also looked at the work done by the elastic force in a spring, as a particle moves from a position of x0 to x. And we'll take the special case where there's no dissipative forces, so on the right hand side we have the change in kinetic energy, and now we're going to take the initial terms to the left hand side of the equation, and the final energies to the right hand side of the equation. And this is the statement of the conservation of mechanical energy, which states that the total mechanical energy is constant in a conservative system. Now if there were dissipative forces acting on a particle, the work done by the dissipative forces is equal to the change in the total mechanical energy. Conservative systems, where there are only conservative forces that do work, and these can be internal or external to the system. So for example, the force of weight or the gravitational force is the only conservative force that does work in the first case, where the track is frictionless, and a normal force acting on the cart, which we treat as a particle, is always perpendicular to the motion, so the normal force does no work. Now for this pendulum, we have the force of weight acting downwards, and a tension force in a cable or rod that's always perpendicular to the motion. So in this case, only the conservative force, being the force of weight, does work, and the tension force is always perpendicular to the motion of the mass, so it effectively does no work. And here we have a spring mass system in which only the force in the spring, which is a conservative force, does work. Suppose we want to find the speed of the particle at point D and the tensile force in a string at point D for this particle undergoing vertical circular motion under the influence of gravity. While at the top of the trajectory, we also have the force of weight and the tensile force. So applying Newton's second law at B, And for the special case where the tensile force in the string is 0, we obtain a critical speed, where the force of weight is mg. And applying Newton's second law at D, so to find the tensile force in the string and the speed at D, we need another equation, which is obtained using the conservation of energy. So taking our reference point at D and doing an energy balance between D and B, we have the initial kinetic energy plus the potential energy is equal to the final kinetic energy at D. So we can substitute for VB into this expression to find the speed at D, and then substitute for the speed at D to find the tensile force in the string. A 10 kilo car initially at rest rolls along a frictionless surface from A to B, and it then travels along a surface with a friction coefficient of 0.5 from B to C. And what's the speed at C? So by the conservation of energy between A and B, the potential energy is equal to the kinetic energy, and from B to C, so what we get is the kinetic energy, which is equal to the potential energy at A minus the work done by the friction force, which is the coefficient of friction by mass by gravity by the distance D, is equal to the kinetic energy at C. And now we can cancel out the mass, and what we get is 9.8 by 10 minus 0.5 by 9.8 by the distance is equal to 1/2 Vc squared. And then solving for Vc, we obtain 12.9 meters per second. A 3 kilo particle rolls up an inclined frictionless plane with the initial velocity of 12 meters per second directed up the plane. And calculate the compression force in a spring which has a stiffness constant of 400 newtons per meter. So an energy balance from A to B gives the kinetic energy at A is the kinetic energy at B plus the gravitational potential energy at B. And then an energy balance from B to C gives the gravitational potential energy at C plus the elastic potential energy at C. Because when a spring compresses up to D, the kinetic energy of the ball becomes 0. And therefore we can equate the kinetic energy at A with the total energy at C. And I encourage you to calculate the compression force in a spring and post your answer in the comments. The power is the rate at which a force does work. So consider this work integral. If we do a change of variables, so now we're integrating over some time interval. And now if we differentiate both sides of this equation with respect to time, well, by the fundamental theorem of calculus, and dr dt is the velocity. And this is the definition for the instantaneous power, or the rate at which a force does work. Therefore, the average power is the change in work on the change in time. So if we consider horsepower, which is the power required to move a 75 kilo mass over a distance of 1 meter over a time of 1 second. So this is force in newtons by velocity, which is the unit of a watt. And therefore 1 horsepower is 735 watts. So effectively, if a jockey weighing 50 kilos is riding that horse throughout a race, then the horse can easily carry that jockey throughout the race at a high speed. Superman has a mass of 90 kilograms on Earth. Derive an equation for his instantaneous power output in terms of the following variables. We'll recall that the instantaneous power is the rate of change of work with respect to time. So by the chain rule, we can write this as the rate of change of work with respect to the y coordinate by dy dt. And we can recognize that dy dt is a velocity. So the w dy is the slope mg, and dy dt is kgt. So we can recognize that mg is a force, and g is in acceleration by time gives meters per second. So basically that's units of joules per second, or watts. Using the diagram below, explain what horsepower is. So horsepower is the power required to move this 75 kilo mass 1 meter over 1 second. So we can write the power is 75 kilos by the gravitational acceleration, and that's multiplied by 1 meter over 1 second. So that's going to give you 735 joules per second, or watts. So as you can imagine, if the horse was carrying a 50 kilo jockey, then the horse can sustain enough power to carry that jockey throughout the whole race. And if we look at this car, which has a brake horsepower of 700. That's the power of the crankshaft, so neglecting the resistance of the gearbox and friction between the moving parts of the engine.